Thanks for hanging in there here for the sort of the tail end of the day. And actually, what I'd like to do is bring us back to the city. And I'm going to talk about structure and nature, but I think more importantly, how the city informs ideas related to design, and how nature might inspire us maybe to do a better job with performance. I'd like to talk about the relationship of architecture and structure to the ground, and challenge ourselves to think about whether we design structures to be permanent or temporary. In cities and what it means to us, the environment, and the relationship between the United States and China, and the inspiration and the battle to try to come up with new ideas to make this a better place. And how cities and people respond to buildings. And buildings don't need to be 100 stories tall to be loved. They don't have to have expressive structural systems. They might have a graphic response that might create a place where people can congregate, maybe share ideas. A few years ago in Amsterdam, there was an experiment that was done that everyone in the city could participate in, but those that were in direct sort of participation wore a tracking device. And this went over a couple of months, and you could watch the movements of people throughout the city. And what you see on the wall on the right is the paths that people took. So the question is, are our cities ordered by the streets that manage the flows of vehicular and pedestrian movements, where areas in between are void and absent of life? Should our structures be restricted to regular load paths defined by elements set up on disciplined grids, ignoring the spaces in between, ignoring their contributions only because an order has been imposed upon us? And should our structures be defined as static objects, or as objects that are in continuous motion? Should we continue to think of our structures two-dimensionally instead of volumetrically? So the city experiment, the tracking of people walked on sidewalks, traveled on roadways that we defined, were the spaces in between not relevant. So we're seeing something happen, and it's real, and people would argue that perhaps it's natural, but most would argue that it's not natural, that we're impacting the environment based on carbon emissions, and this global warming is changing the way we use this place. The Arctic and glaciers are dying. The image that you see on the right is one of two places in the world that houses every sea known to man. And you wonder, what are we preparing for? Is it something that man creates, or is it something that man and this environment and its changes create? When we build buildings, sometimes it takes 20 years for the carbon that we put into our building at the time that we build it to catch up with the carbon that's emitted through the operation of the building. So one of the challenges for us is to think about construction and material and time, because it impacts the amount of carbon that we put into our structures at the time that we build it. And more importantly, over the life of a building. As Steve has mentioned, if we increase the performance by introducing devices or other mechanisms into our structures, we can decrease the carbon that could be emitted because the repair is less. We perhaps don't have to rebuild. So these are the things that we need to think about. It goes beyond just building safety, it's building performance. A few years ago, we had a graduate student that was working with us as an intern. We had an architect in our studio that said that he was interested in bamboo, the form of bamboo. And so I said to the student, I said, there's something really interesting about bamboo. And it's not just that it's beautiful, but it's strong, and we've been using it for thousands of years. And what is it about it that might inform the built environment in a different way? So he went over to UC Berkeley, sorry, Greg, you didn't say. He went over to UC Berkeley to the library and found that, in fact, there was a lot of research that was done on bamboo. Bamboo's hollow, and the bands that you see over the height are diaphragms. The diaphragms are closer at the bottom than at the mid-height, and then they close again as you get toward the top. And you wonder about it and why. Is it random, or is it something that always happens? Well, in fact, it's mathematically predictable. It's not random. You can actually predict the placement of those bands because they're there to keep the walls of the bamboo comb from buckling. So the tighter the spacing at the bottom, the demand is the highest. You got the closer spacing, it opens up where the demand is less, and then it closes again at the top because the proportion of the diameter to the spacing of the rings is such that you get a smaller geometry change. It's also something that can be defined in the diameter and the wall thickness of the bamboo. The equation that you see is an incremental equation. It's actually can be used to define the spacing, the wall thickness, and the diameter. So you wonder when you plot this quadratic equation what it means. If you thought of a structure that was fixed at the base and had a uniform load applied to it, the bending moment would look like this. It's the same diagram that you can extract from this growth pattern of bamboo. So you wonder if this relationship is important, and it's important for us to think about perhaps how it gets applied to what we build. And that's the difficult part. So what we looked at in this case was an incremental spacing of a diaphragm that connects the inside to the outside, and instead of equally spacing the diaphragm, the connection, we used the idea of the bamboo, so it was tighter at the bottom and open toward the middle, and then closed at the top. And what we did is we created this structure that perhaps could be thought of as a shell at the outside that's braced by these diaphragms and tied to the center core. That's the first pass. What we found is we took that shape that's to the right, in the middle, actually, the diagram in the middle, and connected it to the outside and found that this interaction between inside and outside and an irregular diaphragm spacing, in this case also outriggers that would connect, could save the material for the lateral load resisting system by about 15%. Incremental changes, but positive changes in terms of how this building behaves and the amount of material that is used. These incremental segments that you see in bamboo are in other places. And it's a cantilever, it's a hollow section that's braced by a diaphragm that could be mathematically predicted. So what does it mean to our buildings? And China has been very important to SOM, practice of engineering and architecture. There have been some opportunities that have been really unusual. And it started for us largely with two projects. This is one. This is in Shanghai. This is the Eiffel Tower. And the other project was the ICBC project in Beijing. And Professor Fu, who you heard earlier, has been a very important part of the relationship between the United States and China in terms of thinking about structures and the performance of structures from the point of view as an expert. And he also was involved with us in some unbuilt work that happened before this project in Shanghai. So here's a building that has very complicated systems. It uses concrete and steel. The core is an octagon. There are 8 large composite columns on the outside, and structural steel that infills the rest. We talked about creep and shrinkage earlier. The problem of connecting a building as you build it, and the fact that you have creep in the core that's different than the creep in the columns, so that as you build this building and as you tie it up together with these large trusses, outriggers that resist lateral load, wind, and seismic, you quickly find that the outer gets ripped apart under its own displacements as you build it. So we have a problem. We have a project. Popsicle sticks. My daughter, who's now she's graduated from graduate school, and Saturday night was a little celebration beer bottle in the back after building. It's a simple model. The point about this is it's all of a sudden it set off a way of thinking for us, that we could free up these trusses by introducing pins and allowing them to move through this relative displacement for a period of time during construction. And it started with this simple model, and the trick was the slots you see at the top. The model turned into the working drawing turned into the prefabrication at the plant, and then the site, and the scale from that simple pin model to those connections that you see next to the man who was a site representative for us gives you a sense of what these fundamental ideas might mean to construction at a large scale. So the project allowed us to think about behavior, in this case performance, and perhaps in the future this relationship with nature. So what is it about nature? It's a really interesting thing, and I think it's not just about plant growth, but it's about how bodies work, and whether it's your head or your shoulder, it informs other ideas that perhaps get into our buildings. So joints that move like the joint in your body. So curved systems, they make sense when you talk about bending moments and a release of energy, and perhaps through friction. When the demands get very high, instead of keeping the joints locked, they rotate, move, and dissipate energy, but they protect the base building, right? It's a natural response. And it helps us to think about frames, dissipation of energy in a different kind of way. And there's been mention of this in systems, and these are devices, whether it's seismic isolation, or the braces that are unbonded, where they, or as Steve showed earlier, the idea that you have shear wall systems that are partially decoupled from the ground through post-tensioning and damping systems. These are the ideas that set us forth with natural response. So this was our view, looking at Transbay. Fred mentioned earlier this project. This is a good example of a project that was a huge disappointment for us. We entered, we were one of 3 teams. It was a developer-led competition with design and contractors behind each one. But what happened is something special for us. Through the development of that idea, we started to think about building performance. And we started to think about things like the hurricane and the idea of natural growth. And you know, for many of us, we think about the hurricane as an applied force. It's in plan, you see it on the news. And it's an idea where the highest level of force is right at the wall of the eye of the hurricane. And it changes as you go out. And it's mathematically predictable. But the idea is, instead of the applied force, perhaps it's a resisting force. So the center perhaps has the highest resistance, and it reduces as you get out. So we took this idea, this hurricane, we stood it vertically, and perhaps we can think about it volumetrically. But how can we define structures that look to natural growth and natural performance as a way to make our buildings more efficient? A few years ago, I went to this place with my daughter, and I have three girls, and I had this little small requirement when I started college. I said that you have to go on a trip with me, and it's not a vacation. It's going to a place to learn about art and architecture and maybe a little bit of engineering. I don't have any engineers, by the way. The three girls aren't engineers, so I've scared them off it. But anyway, we went to this place, the Eiffel Tower, and Ahmed talked about this earlier. We got to the plaza, and on the upper right, near the base of the structure, is where we entered. It was the stair. I said, if you want to see this building, we need to walk it. We're going to walk the stairs. And we walked up to the top of the first platform, and probably several of you have been to this place. And we looked down, and this is what we saw. It was the line, the people in line for the elevator. So this is the place where people line, and this is I'll call it the least energy of that placement. And again, it's not random. It's embedded in our DNA. So this natural pattern is one that I think is important for us to study. So for our proposal for Transbay, we looked at this and we thought, well, the placement of material might be something that's much more sophisticated. And at the time, a friend of mine who's the head of the San Francisco Theological Seminary in San Anselmo, he wrote this, and you can find this, I think, online, but for his incoming students, one of the pieces that he said, what if you could develop strong, flexible, responsive, adaptive, sustainable human beings based on the intrinsic architecture of the hurricane? Buildings that are in harmony with, instead of trying to resist and stand up against and conquer, the powerful creative forces that might otherwise threaten and endanger us. In other words, why stand up in a way that's so resistant? Why not think of this coexistence between structure and force, and try to come up with the best idea? So that's what we did. We took the concept of Mitchell that was developed in the early 1900s, and we looked at this building in a way that you could open the base, you could create density of the frame at the bottom, and then open it toward the top to come up with the most efficient system. There's a theory that's been around for a while, and this is probably, some people will say, well, this is kind of nothing new, it might just have a new name, I don't know. It's a theory of emergence, and it's this idea that the collective of similar elements when working together are far more powerful than when they're working alone. And so the idea, and when it's influenced on boundary conditions, some type of condition, and in the case of the termite mound, it might be the environment and the fact that these mounds are super cooled, or birds in flight to cut down resistance, air resistance, or cities, or this place where people collectively create greater ideas. And this energy that gets created that is far more powerful when working together. So if we think about material and the placement of material in our buildings, how can we do a better job of minimizing the amount of natural resources that we use? And think about buildings behaving from the very raw sense, right? So the idea of a building not thought of as beams and columns anymore, but perhaps a three-dimensional form, or at least a surface where you apply load and you optimize the behavior, in this case looking at lateral load and support conditions at the base. So the red that you see is areas of highest demand and blue least demand. But all of a sudden you start to see something that's perhaps far more organic and not expected. So what is it about this behavior and nature? And we've been experimenting with these ideas about raised systems and looking at and never assuming that we've done before is the most efficient way of design. So structures that have bracing systems that are not concentric in tall buildings anymore, that have this sort of high belt idea of three-quarter, one-quarter geometry. And not just taking that idea and applying it as a literal response, but looking at perhaps varying the density, making the systems denser at the base where demands are highest. The orientation of the bracing system is more vertical, where the gravity demand is high. And trying to come up with a way that takes the information about behavior and think about it and interpret it into something that might be beautiful. So this is the response with a single point load at the top of this form and 2 points of support. And the response on the right is what you get from it. So buildings perhaps will look differently. So the building on the left is my favorite building, and it's in Chicago. The reason why it's my favorite building is because we sort of stuck our necks out for something that was super tall, and we tried to come up with a way to manage wind and gravity loads so that it was super efficient, and 2 buildings, 2 towers, became 1 tower because the amount of material in that building was about the same as it was for the lower buildings. But maybe the building will look differently. So the building you see on the right is actually under construction in Shenzhen. And we hope within the next year or so, the structure will be well along and we'll see this framing system at the perimeter of the building. So it's one of these things where you dream about maybe where we're going, and then you think about, well, maybe there are other applications like bridges. So, the Warren Truss or the Pratt Truss or these things that we use all the time, we think they're the most efficient to span long distances. In fact, they're very efficient. This is at LAX at the airport in Los Angeles. And if you take the building and you turn it on its side and you mirror it about its center point as a simple span, so support on each side, and you take that tall building concept and connect it, you find that geometry yields a far more efficient truss than the other. So these are things that are in progress and ideas that might yield a different way of looking at truss systems, maybe in 3 dimensions. But maybe we should be thinking about 4 trusses in this way, right? I mean, we just go at the simple truss. We've drawn it 1,000,000 times. But maybe the geometry of these trusses should be much more of this asymmetrical position of framing along the length. So a couple more ideas. Back to the city. This is Guangzhou. Everything that you see in white is planned. Okay? The brownfield site, for the most part, the planning group has been instrumental, not just here locally in San Francisco, but also overseas. And how do you sort of create these cities that are done really responsibly? And cities are about data. And I think data is something that is wonderful if we can figure out a way to manage it. We find it in our own firm. We have information that people generate every single day. Just to get our arms around this is really, really super difficult. Others at universities and practices, I'm sure, feel the same way. But what if we thought about our cities as fields, as I call it sensory fields, where seismicity and wind is understood in a better way. And if we're able to monitor the field, perhaps it can inform the building, the city, in terms of how we design. And when we design buildings, we do all this really fancy analysis. It's super sophisticated. We design, we create drawings, we build buildings, and we take the analysis model and we put it aside. In fact, most models you can't ever run again after a certain period of time because software programs change and so forth. But what if we came up with a way to tie the analysis model to the ground? So in other words, if your building understood and you were able to mirror the building's performance with your analysis model, perhaps the analysis model could be embedded in the idea of building performance. Because we know where the demand is. We look at a zillion different load combinations, a zillion different directions. But if we understood the magnitude and the direction of force, perhaps we could change the building at a moment in time where it's important. And, people think this is kind of nuts, but there is maybe a way to take and separate the building today, because yesterday somebody would say, well, what happens when the power goes off and I try to create a magnetic levitated field? Well, today I can argue that there are technologies that with energy storage that in fact could enable us, if we understood the oncoming ground motion, we could perhaps come up with a way to decouple it momentarily with the energy, the backup energy source that would provide the power to do something like this. And perhaps we can have structures that are self-reflective. This is in Berlin. This is the same daughter, by the way. This is the next city that we went to. So she was on this pedestrian bridge. It's at TU Berlin. It's a carbon fiber stress-driven bridge. So the idea of introducing air into the handrails was enough to change the behavior. So using really super high strength material is not something that's so far reaching. So material that's so high, has such high strength and is so active, when we put load into it, perhaps can be controlled by these devices. And systems that are rheological. So buildings that we create perhaps are conduits for liquids. Not a new idea, right? But if you take buildings that we design today, and this is one of our projects that is almost finished with construction now, almost, it's really finished and more or less starting occupancy. Perhaps this building, which actually Todd C. talked about earlier, that has some really smart, sustainable ideas where it's a double wall system and air can flow between these two walls. Forces flow very well around this structure, and it's a very efficient way. No columns. It's a 4-story diagrid bracing system. But what if, instead of filling these tubes with concrete, we fill it with liquid? But the liquid perhaps can be changed in a phase change when demand is high. So stiffness might change over the life of the building. And responding to demand, liquid to solid, is kind of the most basic idea. But material that perhaps can go through a phase change, it could be electrified, it could be changed with some outside energy source. And cities, and the reaction to planning, and how do we think about material and efficiency. The areas that you see in blue in the diagram on the right are areas where we drop below a minimum threshold for efficiency that we target. Let's say it's 80%. So structure, mechanical systems, elevators, all impact usable area. And we can think about this and plan cities based on the material type, carbon, perhaps geometry, the efficiency of the use of the floor, solar exposure, and maybe do it all at once. So the plan is just perhaps not a sight line only or shadows, based on site and geometry, but it's much more comprehensive. That we look at materials and we're really sensitive ultimately to the environment because of these other impacts, these parameters. So what if the structures of the future can be designed based on sustained forces by using materials that internally flow in response to transient loading, increasing in density in areas where necessary? What if the behavior was three-dimensional, considering the volume of the structure, rather than just its perimeter? And what if the behavior emerged through a central controlling force of a collective intelligence? So what is it about these ideas that advance geometry and the architecture of these projects? So there are a couple of things that maybe are worth looking at. I don't know. These ideas are sort of, how should I say it, contemplated in a couple of documents that just came out. The one on the right actually is a second edition of a book that was written for this place, for Stanford, and it was a book that was originally class notes for an integrated design studio that we did here at the university, and it contemplated architecture and engineering as one, and it looks at these complex ideas at the end, and in the beginning it looks at some very basic site issues and what we consider when we start designing these types of projects. So back to the ground. You know, we do all these sophisticated things, and we're making great progress, but there are the things that work that we do around the world. This is in Shenzhen, and what you see is a group of people that build these caissons one by one. And the most important job is actually the job at the top. And it's usually a family, it's usually a brother and sister, or perhaps two brothers, husband and wife. And the job at the top is one that keeps material from dropping into the hole at the time that it's being hand dug. This foundation system works, and this foundation system is what several tall buildings will sit on, or in fact have sat on by this time. So you wonder, when we look at these designs and these concepts about nature and the sophistication of these principles, the basic ideas, I think, are very important for us to come back to. The ideas that work. But it doesn't hurt to dream about things, to dream about tall buildings and projects that may never happen, who knows. But this idea of trying to come up with solutions that look different, and maybe are more efficient, that maybe hopefully are more beautiful, that contemplate nature and things around us and try to interpret and apply these things to things that we actually can build. So anyway, that's what I have. Thanks a lot for hanging in there. And Professor Dearline, please.
Thank you, Mark. I can't think of a more wonderful or inspiring way to end this day. I wanted to do three things before we leave, and that's just to give some acknowledgments again to kind of our organizing. Again, this was something that was really conceived at first by SOM, teamed up with us at Stanford and with the group CTAS from China, kind of working together. And behind the scenes, or in front of the scenes, was really John Zhang on SOM, pulling together a lot of the program, contact with speakers and so forth. And Raquel Hagen, who snuck out to the back there, who's here at Stanford, who really took care of all the logistics. There you are, Raquel. So I'd like to really thank those two people, John and Raquel, for just helping put so much of this together. Raquel's been helped by many of the students around here today, so appreciate your guys' help as well, and girls' help. Next, I'd really like to acknowledge the speakers who really kind of stepped up, accepted these invitations, traveling short or long distances to get here. But I think really put together kind of a fabulous set of talks today, touching on kind of all aspects of the problem. So I'd like to give us a round of applause for all the speakers we had today. And finally, the last thanks is for everybody here, to you, the audience, because I think this is really kind of what makes it happen. I think we're really, it's very delightful to kind of see the amount of interest this has generated. And as we see, this is, as Mark's talk gave, this is kind of the beginning of the discussion. I mean, there's so much more left to do, and cities are going to continue to grow and evolve and so forth. And, now if you've been around this area, the South Bay here, you'll know the traffic's horrible now. So if you hang out here for like another 45 minutes, we got a little more food brought in, some drinks in the back there. You'll have a much more pleasant trip home. So why not hang out a little bit longer with friends and kind of reflect on the day, kind of have some discussion and so forth. So thank you, everybody.